Hey, welcome back to Fat Mama Physics. In this video, we are going to talk about linear relations. That is 5.2 of graphing, the next section after looking at different kinds of patterns. I did say that at the very beginning of videos, I will introduce a new board game that I currently play or have played. Because in this lesson, we are going to talk about independent and dependent variables, how they relate to graphs, how one thing depends on the other. The board game that I chose is Pandemic Legacy. Okay, let's take a look. We fit this on screen. Pandemic Legacy, you might have heard of the base game, Pandemic. Pandemic is a co-op game in which players come together and they try to eradicate diseases around the world, which are represented by these different colored cubes. Pandemic Legacy, however, is it's one of these legacy games. Is basically you play a series of games starting with the first one, and whatever happens in the first one is going to affect your second game. In this particular set, I will show you the board. Is depending on how your game plays out, the events that turn out in the next month may change. In Pandemic Legacy, there's a total of 12 months, so you play for the whole year, and every month new things happen, which might surprise you, and you might have to change the way how you deal with things. How well you've dealt with it in the beginning of the game might affect how it turns out to be later on in the game. So all this dependency might come back and haunt you in the later game if something happens. So here's the board. If you can see the board. Okay, so the board is pretty much the map of the world, and compared to the original Pandemic game, it might look a little bit different because notice our board has permanently changed depending on the decisions we've made, things that we've done and not done, which will affect our games later on. I am not going to show you the details of the board because it's a big spoiler, so those of you who do want to play it later on will not have a chance to be surprised by the game itself. But I guess one thing I can kind of sneak peek with you is the following. So I probably can show us kind of zooming in to North America, and you might notice, you might or may not notice, depending on how good this camera is, you might notice that beside every city there might be a number that you see. So that number that number is a sticker that we put on the city. I won't tell you what it means, but essentially every time things happen, we put on stickers onto the board, which then permanently changes how we interact with that city and whatnot. So, yes, details on that for you to figure out when you start the game. And so in this game, you play as different characters. They have different roles. For example, there's a researcher, scientist, medic, journalist, dispatcher, quarantine specialist, etc. Oops, I think I gave out. Anyways, the cool thing is you can decide their names. We had a colonel, and we named him Saltai. Some of you might or might not know the reference. So you get to decide his name. Another spoiler. Sorry. And essentially how the base game plays is that, yes, you go around eradicating diseases. Every turn, new diseases show up in any of these cities, and you kind of have to go there, tamper it down before there's so many cases where it leads to an outbreak, and outbreaks are never good. It's it turns your world on fire. Essentially, you have to tamper all the flames down, which is a lot of work. So that is kind of the game. So notice the theme here is that what you do earlier in the game is going to affect your outcome, things that happen later in the game. So later game depends on decisions you made earlier in the game. The idea of dependency, which is related to what we will be talking today. All right, so I'm going to put this aside. Oh, another thing I can tell you about Pandemic Legacy. There's Pandemic Legacy 2, and 0 is coming out. I think it's already came out. We're excited to buy it. But yes, we've played through 1, Pandemic Legacy 2. We're excited about 0. It's a great... it's actually ranked near the top on Board Game Geek. I think 2nd or 3rd. At least the first season is. Anyways, let's... get started with today's lesson, which is linear relations. You might have learned about something called the independent and the dependent variable in your science classes. And math, we're going to touch upon it again because we get to see how we can turn your data from your experiments into a visual representation, which is a graph. Specifically, we're going to look at linear relationships. So on a graph, what that looks like is you'll see a straight line cutting across. So what does that mean? It means if I increase my x-axis by a certain amount, my y-axis value will also increase by a set amount every time that I change my x-axis value. So what does that look like? Let's look at an example here. Below I have a table, example 1, where we have time versus distance. And let me give you a little bit context for this table. So imagine at t is equal to 0 seconds, this person is 1 meter away from his house. The next second, this person is now 4 meters away from his house. So imagine I have a house, okay? And then right at the beginning, let's say this person's walking to school. He's 1 meter away. After another second, he walks 3 meters, 1 meter to 4 meters, so that's 3 meters away more from his house. The next second, he walks another 3 meters away, which is now 7 meters. And then after another second, he is now 3 more meters away at 10 meters. So notice every second, he's always increasing his distance from his house by 3 meters. This is called a linear relationship. Okay, it's a constant change. A constant change in one quality, which is your x, produces a constant change in the related quantity, which is, in our case, our y. So this is why we call this the independent variable versus the dependent variable. And notice that for time, as my time goes on, as I look at the time and as time passes, this person is going to get further and further away from his house. That's the dependency. His distance away from the house depends on how long the time has passed. So that's the idea between independent and dependent variable. Here we found the pattern. As x increases by 1, okay, the y increases by 3. Okay, so that's kind of the idea here. Okay, by 3. Oh, if you caught me in terms of units, you're very good. As I increase x by 1 second, my y, the person, increases his distance from the house by 3 meters every time. So that is the idea here. Okay, so here we want to do a few things. Now, in this particular, in this lesson, we want to look at the dependency, but ultimately we want to see what this looks like on the graph. So there's a couple way to do this, but I'm going to go with the dry nuts and bolts of how to put this on the graph. Here we have a table, and here it says we should write the equation for this table. And this is kind of review from what we did in the last lesson, but let's just go over how we should do this, okay? So first of all, we know that every second that passes, which I'm going to say my variable for, I will use x, for example, for time. I will use y for distance. My y is going to depend on my distance. My y is going to be on one side. My x is on the other side. I don't know what that's going to look like. However, I know that as my time increases by 1 second, my distance increases by 3. So if I have x, this is most likely 3 times the amount of seconds that passes by. Which means if I have 2 seconds that pass by, my person is going to be plus 3 plus another 3 away from the house. Plus 3, and the pattern keeps going. Okay? So it's likely that's going to be our starting pattern. However, if we take a look at this equation, if I put time is equal to 0, okay, then y is 0 is as x times 3, that's going to be 0 for y, and that doesn't make sense because this person actually started off 1 meter away from the house. So how to make this equation work for, say, time is equal to 0? we have to put a +1 here, because if this whole thing is 0, y must be equal to 1. Okay, well, you might be wondering, well, does it work for the next one, the next second? Well, let's try it out. If if x is equal to 1 for 1 second, then we get 3 times 1 is equal to 3 plus 1 is equal to 4. Hey, that works. Let's try for the next one. 3 times 2 plus 1 is equal to 7. Okay, there seems to be a good pattern here. Okay, sure, this checks out. This works. So that's our equation for this dependency. Notice my dependent variable is usually alone by itself, and it's equal to some manipulation that you do with your independent variable, which is your x. So that's like the last unit. Now when we want to plot this on the graph, there is the dry and dirty way, the basic way, which is to plot the coordinates onto the graph, and we can generate all these coordinates from the x and y values, your independent and your dependent variables. So here we can write them down. On your left side is going to be your x, right side is going to be your y. So for example, the first one will look like 0, 1, and separated by comma. So 0 is here, that's your x, this one is your y. Okay, then we have the next one, which when time is equal to 1 second, y is 4 meters away from the house. You might be wondering, why do I not have units for this one? For the purpose of this graph, we are just going to put in these coordinate pairs. I don't want to confuse you with too many letters and symbols. However, you'll see on the graph how we can designate all of these values in terms of its units, how we label our axes, etc. Okay, so here we are. We have all our coordinates. Now we can plot them on the graph. Now, I know that graphing, especially when you have to chop your graph down into pieces to have the right size graph, is a little tricky. So I'm going to do a little review with that. Now, when you first get a graph, and when you want to draw a graph, depending on if you're in science, if you do science, you ideally want your graph to take up as much space as possible. So if I plotted all these dots and it turns out I end here, that's a tiny little graph. No one can see that. It almost defeats the purpose of drawing a graph, because you want to visually communicate information to people. If you draw such a tiny graph, no one can see what the relationship is. So you want the graph to take up as much space as possible. So I am going to try to use this whole space. I should have a title here. This is the distance. This is where my science influence gets to take in. You want a meaningful title, and you want to underline your title, hopefully with a ruler. I don't have that luxury right now. And so that's your title. Make sure to label all your axes. So here we have time as your independent variable. Notice your independent variable always goes in the x-axis. I mean, that's just a guideline that we highly recommend you use. Time in seconds. And then over here, this is your distance measured in meters. And then I'm going to label this line as my x-axis, up here as my y. So notice that I've put the units in the axes themselves. So it tells me the numbers that are along my line, these are measured in meters. They're measured in seconds, whatever that is. And and you might be thinking, yeah, they're kind of like number lines. That's true. I have one number line going one way, one number line going the other way, showing you the two dimensions. And of course, sometimes dimensions aren't necessarily in the same category, like distance is definitely not the same. You don't measure length with time. That's kind of what I'm trying to say. Okay, so now we have this. Okay, let's take a look now. What we want to do is we want to now give these gradients here values. The first thing you might think, oh, can I just do 1, 1, 1, 1, 1, 1, 1, 1? True, you could do that, but notice the time. The time goes up to 5 seconds. So 0 is here at the origin, 0, 0. Then 1 would be here, 2, 3, 4, 5. You only take up that tiny bit of the graph, which I told us is not what we want to do. We want to take up as much space as possible. So here's what I'll do. If my time value goes up to 5, which is 0 to 5, then I want 5 to be as closer to this end as possible. I kind of have to chop off, I might have to extend the range here. So, or think about me taking the numbers and stretching them out, meaning 1 second might take up, say, 2 to 3 spaces. So let's count the spaces in total to see how much we can stretch it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14. Now, it's not 15. 15 means I could triple it, or I can use 3 spaces. But basically, that kind of goes up to about, I might be able to use 10. Because why? If I use 10 of these grid lines, which means every second is represented by 2 spaces. 10 divided by 5 gives me 2 spaces each. So here, this is going to be 1, this is going to be 2, let me zoom in. That's 3, 4, and here's going to be 5, okay? So that's kind of how you chop off your graph. You count how many total spaces there are and see based off your total how you can divide that over the amount of gradients that you want. Sometimes you might need to use a lower number depending how nicely things divide. I could take 14 divided by 5, but I'm going to get really ugly numbers. So I don't want to do that. I give myself a hard time drawing my graph, okay? So that is the x-axis. Now for the y-axis, I believe we go from 0 to about 16, I suppose. Okay, double check. Okay, that is 16. So let's count the grid spaces here. We might be lucky. 1, 2, 3, 4, 5, 6, 7, 8, 10. 1, 2, 3, 4, 5, 6. Oh, we are so lucky because we don't need to change the intervals on this graph. So this will just be 1, 2, 3, and I'm just gonna... Okay, so this is kind of how I set it up. Now, be very careful when you do set up your gradients. You need to make sure that the same number of boxes equals the same interval as you move across. So let me show you what some of my students like to do. Tell me what is wrong here. Good time to pause the video and think about what did the student do wrong. Okay, so if you said that the intervals are inconsistent or something along the meaning of that, you are totally correct. So if you take a look at the x-axis, what this student did was 1 box is equivalent to 1 second. Then the student said, oh, I changed my mind. Since I have so much space, I'm gonna make 2 intervals equal to 1 second. Now the spacing is inconsistent. And we don't want that. We want to make sure the intervals stay consistent as you draw the rest of your graph for that 1 number line. You might have a different interval for your x versus the interval for your y, and that's okay. But as long as it's along the same line, the intervals must stay consistent. Okay? So this is a big no-no. No, don't do this. Gonna leave it on the screen for like 1 second. Okay, so now we can draw our lines, the dots on our graph. Okay, so let's start off with 0, 1. So the 0 represents the x, 1 represents the y according to that. So then first here I have 0. So I go to my x-axis, I go to here. The x along the x-axis, 0 is right there. And then I go to the y-axis, which is 1. Then I look in the vertical direction. 1 is right there. So my first dot is going to be right there. Probably use a different color here. Okay, so that's done. Now if x is equal to 1, y is equal to 4. So I go along my horizontal line. I identify the 1. 1 is right there. And then I move up to where the 4 is on my y-axis. That is where my next dot is. So notice when I'm drawing my dots, I'm looking at the x-axis, the horizontal line for my x, the vertical for my y. Second one is 2. Okay, and my x-axis is right there. Now if I want to identify my y, which is 7, I go all the way up to here. That is my 7. So that's my next dot. 3 and 10. So 3 is here. I go all the way to 10. 10 is right there, and I put my dot right there. Okay, so notice that if I match up my y, I match up my x, that these tell me where my coordinates are. Okay, next up is 4 and 13. 4 is here. and 13 is right up there. You don't have to draw these dotted lines for your graphs, but I'm just drawing them for the sake of you visualizing where these are. 5 and 16. So 5 along the x is right here. I move up. I find the 16, which is right over here. Okay, so this is my scatter plot for my graph. The pattern here is each point on my graph is, so every time I increase by 1 second, I increase my y by 3 meters. So 1 second over, 3 meters up. 1 second over, 3 meters up. So notice that pattern here. And you might think that, oh wait, there's 2 boxes. But remember, we set 2 boxes as equal to 1 second based off our line graph, based on our x-axis. So that is how you would draw this one. Now, if we could draw a line here because this is a continuous graph, meaning if I were somewhere, actually I'm going to draw my line right now, okay? Because if I were somewhere, say, 1.5 seconds, I should be able, I'm still moving in between 1 second and 2 seconds. I'm still moving away from my house. So if I try to find where I was after 1.5 seconds, I could technically look at this graph and kind of make a judgment call that's roughly about between 5 and 6 meters away from my house. So time continues to move. Continues to move between each dot. So it just means this is a continuous graph, and as time progresses, I'm continuously moving away from my house. So that is why we can draw a line. In this case, the dots kind of line each other up very nicely, so we can just draw a line through them. When you do experiments in science, you might have data points that are all over the place, but the general trend is a linear relationship. And that's just because there's small amounts of error in the experiment, which means that you are going to try to fit your best fit line through these dots. So that is basically what I want to show you in this video, is how to transfer your data points onto a graph. We have one more example coming up, so stay tuned. Thank you for watching. I'll see you next time. Fat Mama Physics signing out.